Okay, so we only have 4 days of class. We only have 4 more class meetings. That's including today. So we have today, then we meet again next Tuesday. Then we have Thanksgiving break next Thursday. We don't have class. So then we come back the following Tuesday. We have that Tuesday, that Thursday, and that's it. We're done. Then we take a final on the following Tuesday at 11 a.m. right here until 1:45, even though you may not need all that time. All right? So what we need to figure out is what we're going to do about this exam 3. On the schedule, it says we're going to take it on Tuesday, which would be next week. All right? Which I'm okay doing that. The only problem is that I don't have like a formal review handout to give to you to get you ready. We could go through and start reviewing today, but it would be more like, you know, I just put problems up and then you look at those problems, if that makes sense. Does that make sense? Okay. The other option would be to finish up with some material today on logarithms, and then on Tuesday of next week, we would have like a full day review that day. But then you have Thanksgiving, and then you have to come back the following Tuesday and take the test. So what do y'all think about that? The other option would be to push it all the way to Thursday, which would be the last day of class, and have exam 3. But that means there would be, these 2 days would be continuing with more material. So which of these options look the best? Does everyone understand the options? How many of you want to take it next week, Tuesday? Show of hands. 2, 3, 4, 5. Okay. How many of you would like to take it the Tuesday when we come back from Thanksgiving? Okay, that looks like a majority. How many of you don't even want to take exam 3 or a final? Okay, there we go. All right. Anybody want to do it Thursday? Just not next week, yeah. Okay, let's try it out. Okay, let's do this. The one I've circled. Our exam 3 will be the Tuesday we come back from Thanksgiving. So while you're sitting there doing whatever you're doing over Thanksgiving, eating turkey, hanging out, watching football, oh no, this class, y'all don't like sports, right? So whatever you're doing over Thanksgiving, you can sit there and study, because I'm going to give you a review next Tuesday. Right? Okay.
So you can give the review for the final?
Yes, and that'll allow us to come in on Thursday after this test, and we will talk about the final. So if you look at it that way, we're kind of like, there's not much more material I can cram in here. I've got to get a test in here, I've got to get 2 reviews in here, and I've got 1 day. That means today's the day, right? Today's the only day that I really have for like new material. Now, I'm going to squeeze something in here, all right, that I'm going to want to put on the final that we haven't talked about. So, and that's systems of equations. But I think when you do them, you'll be happy that they're there, because they're relatively easy. So, all right, that's the plan. So be here next Tuesday if you want to review for the exam. All right, so we are going to continue with logarithms. Any trouble on the homework, the problems I gave you? Everyone understand how to use their calculators? Any issues? Yes.
I have a question on this C log of 5.
Base 5?
Base 5 of 525.
Log base 5 of 525. This one? What did you get on the calculator?
That's all, we don't use the calculator now.
Not supposed to. Oh, I know the problem. Yeah, you should have had a problem on this one. Because I meant to write 625.
Oh, okay.
Yes, so that you could not do by hand.
Yeah, it was
okay.
343.
That's my fault. But okay, you did on your calculator. If you did it that way, did you do natural log of 525 over natural log of 5? Is that the way you did it on your calculator? Okay, and that gave you approximately, what, like 3 point something?
3.89.
3.89? Okay, my mistake. If that would have been written correctly, 625 is what I meant to write, then you would have to realize that 625 is 5 to the 4th power. And then you're saying, remember, this means 5 raised to what power is 5 raised to the 4th power. So your answer would just be 4. Okay, any other issues?
I had an issue with the log 10.
Okay. What part of it? Was there, can I see which one you're talking about? Log 10? Okay. So what is log 10? That should be 1. Now the reason it's 1 is because if we don't write the base, Brianna, if we don't write the base is understood to be 10. Okay, so another way of writing this would be log base 10, 10. Those are the same expressions. And then you're asking yourself, 10 to what power is 10? So 10 to the 1st power would be 10, wouldn't it? So your answer would be 1. All right, anything else?
Did you press record?
Yes, I did, thank you. I did this time. I did it a little ahead of time. Natural log?
Yeah, natural log with the
Natural log of E? Okay, so natural log of E, if we were to try and do this without our calculator, this really means, does anyone remember what this means? It means log base E. And then what am I putting inside of this? E. So we're saying log base E of E. That means E to what power is E? 1. But this natural log of E equals 1 is really an important equation. This came up, actually I gave a Cal 1 test yesterday and that was in there. Natural log of E is 1. Something that comes up quite a bit. So this and log 10, if you think about these two problems, they're the exact same problems. We're taking a log where the base is the same as the thing in here. Right? The base is the same as the thing in here.
So log negative 10, it's still 1.
If this was negative 10, you can't put a negative in a log.
So it would be nothing.
It would be undefined. And that's where we got an error on the calculator. And that goes back to the idea that the graph of logs look like one of those two. And we had the vertical asymptote like this. And so you can't try and put negative numbers into logs. Just doesn't work. Okay. I don't think I explained this or stressed this to you last class, that how much I do not like these two notations, log and natural log, that I don't care for these. To me, in my opinion, it would be better if we just wrote log base 10 of 10 and then log base E of E, because when you take these bases out, students get lost. They forget what the base is supposed to be. These are the only two logs that we do that for. Every other log, we always write the base. Okay, if I want to do log base anything else, okay, I would have to put the base here. These are the only two that don't. So I'll just let you know the reason why we do it, okay? There is a reason why we take these bases out, and it's really kind of ridiculous when you think about it. Has anyone ever used a typewriter? I doubt it. Y'all know what a typewriter is? Old school typewriter. You were going to type up a paper, right? You get your paper, you'd feed it into the typewriter, you'd turn this thing called a drum, it'd feed your paper through, and you'd sit there, you'd press these buttons, and these mechanical arms would come up and hit your paper and print the letter on your paper, right? That's the typewriter. So, what's that? Well, hey, I'm just making sure. I want you. No. I want you to think about it. Because have you ever tried to do a subscript on a typewriter? Okay, so that's what I'm getting at. I want you to think about the mechanics of a calculator, the arm coming up and hitting. If you, in scientific research, these logarithms come up a lot because log base 10, I told you what, 10 fingers? And then natural log e, I told you that was that real special number that just kind of works and we don't know why it does, but it does. So if you were writing a research paper, you were a chemist or a physicist or a biologist and you were doing some research and you're using all these logarithms and you're trying to write this 400-page paper to present at some conference or something, then you would have to type it up. And when you type it up, if this symbol appeared in your paper, 1,000 times, while you're typing, every time you do a subscript on a typewriter, you type it, then you have to turn that drum, just like a little half rotation, type your 10, go back, and then continue typing. And if you have to, that slows you down, doesn't it? So what they decided was that, look, if you ever have these two logs to speed things up, just write log, we understand that means log base 10. Write ln, and that we understand that means log base e. It's kind of a historic thing with typewriters. It really doesn't have a lot to do with anything other than that. I mean, because what's the big deal with writing the 10 down there, right? What's the big deal? It's more because of that. So, and it never went away, and that's why we still have it. And to me, I wish we would just go back to this because it's confusing when the base isn't there. But then now, if you had to type a paper and you had to put this in there 1,000 times, what would you have to do? Word processors aren't that much quicker when it comes to subscripts and superscripts. Yeah, if you've ever used Word or for subscripting, it's still not a natural typing move unless you learn the shortcut for it. And it's not something that you just flows real nice. So anyway, okay, that's why it is that way. Nothing we're going to do in this class is going to change it. So today we're going to talk about properties of logs. And what I want to do is before I get into the properties, I want to put up here the goal. All right? What is the goal of what we're doing here? The goal is this word problem, right? You wish to invest, let's say $8,000 into a CD. A CD is in a bank is a certificate of deposit. That means you put money in and they hold that money. You can't touch it for a certain amount of time. So it's like, I'm going to give you $8,000. The bank says, okay, but you can't come asking for it. And you decide how long it is that you have to wait. So it can be a 1-year CD, it could be a 6-month CD, it could be a 5-year CD. And the longer you let them have your money, the higher the interest rate is. So does that make sense? It's like, I'll come back for the money later. All right. And so what do they do with that money? They go take it and loan it to someone so they can have a credit card and go buy their TV, right, at 28%. So you wish to invest $8,000 into a CD for 5 years. In other words, you're going to leave it in there. You've promised you're not going to touch it for 5 years, right? Interest is compounded continuously. Do you remember what that meant? That was a special formula, right? That was that one, there were two formulas. That was the PERT formula, right? So that's telling you in the PERT formula, it says interest is compounded continuously. What interest rate must you get to have at least, how much money would you like to have after the 5 years? What's your goal? You want to put it in there for 5 years. How much do you want when you get it back? How much money do you want to have? Let's be realistic. Don't say like $1 million.
Like double.
Double it? You want to double it? Okay, at least 16,000. Now this is never going to happen. You're not going to find an interest rate. But this is the question. If I want to go stick some money into a bank and not touch it for 5 years, what interest rate do I need in order to get my money to double in that 5 years, right? Go from 8,000 to 16,000. Does that make sense? So let's see what we could do in the formula at this point. We know it's this formula, right? The amount is PE to the RT. What was the P in our formula? The principal, that was the amount that we started with. What is the amount we started with here? 8,000. Okay. E is the number, right? That doesn't change, that's always E. Okay, R is the rate, and we don't know what the rate is, right? That's actually what we're interested in knowing, right? What interest rate do we need? So R we don't know. Do we know T? 5 years, right? So T is 5. Do we know the amount we want at the end of 5 years? 16,000, right? So what we have, if we look at this formula, if we replace A with 16,000, and we replace P with 8,000, we have E, and then here R times T really turns into R times 5, so I'm going to put 5R up here. Y'all see that? 5 times R? R times 5 is the same as 5 times R. Now, we want to know what R is, right? So we look at that and we're trying to ask ourselves, what is R? Well, this equation is something we've never, ever, ever had. We've never had an equation where the variable that we're solving for appears up in an exponent. We've never had this. All the different equations that you've been asked to solve, at least in this class, we've never had an equation where the variable that we want is trapped, it's stuck up in an exponent. Everything we've always done, the variable has been down on the bottom. For example, if I ask you to solve for x here, there's a process, right? You'd move the 1 over, you divide by 3, you're done. But the x is down, it's not up in an exponent. If we were asked to solve this, that's a quadratic equation. You could factor this side, right? Or you could use a quadratic formula. But either way, the x was never up in the exponent, right? This right here is called an exponential equation. And what the properties of logs that I'm going to give you today, the reason why I'm going to give them to you is because it will allow us to solve this. It will allow us to figure out what that R is. And believe it or not, we're going to need a logarithm to do it. All right? So that's the goal. So we're going to keep that. Let's just put that on the back burner. We'll come back to it. Let's talk about the properties of logs. All right. There are some really nice properties of logs. We've discussed a few of these already, but I'm going to write them down formally. First property of logs that I want you to know is that if you take log base A of 1, the answer is always what? So tell me in words what I'm asking you. A to what power is 1? 0. Okay, everyone agree with that? That works for any base, right? Any base, that property is true. Now, in blue, right next to this, I'm going to write the same property, but for the two special logs we have. So log of 1 would be 0, right? That property says log of any base. This is log base 10, but the answer is still 0. And then the other special one we had was what? Not log, but natural log, right? Natural log of 1 would be 0. Do you understand what I'm doing here? I'm giving you the general property for all logs, then I'm showing you specifically for the very two important logs the same property. All right, let's talk about the second one. Log base A of A, what does that equal to? 1. Because that's saying A to what power is A? 1. A to the first power. How would I write that same property for the blue one, for the LOG? Log, we know it's base 10, but what would, 10, this is 1. And that's the question that you asked me earlier, right? Now, in terms of the other special function, natural log, this would be natural log what? E is 1. So just remember, there's a 10 down here, so this is saying log base 10 of 10 is 1. This one is saying really log base e of e is 1. All right, next property. Log base a of a to the x equals, all of these we've discussed in some way in the last class. What's the answer here? X. Because we're saying, hey, a to what power is a to the x power? So x. What would this one be? Log of 10 to the x is x. And this one would be natural log of e to the x is x.
So anytime the x is in there, it's within x.
Not always, okay? Pay attention to what the property is saying. What if I wrote this? Log base 5 of 4 to the x. That is not x. This and this have to be the same for that to be just equal to x. Make sense?
So it does become, like what does it become when it's not x?
Well, this would be different. We can't, this would actually turn out, this really means 5 to what power equals 4 to what, to x, right? That's what this is saying. And that's something we can't handle, okay? That's why the property is important. The property, well, we can handle it. We're not going to handle it in here, okay? But the property is saying as long as the base matches what's going in here, then this power right here, whatever it is, will just drop right out. They undo each other.
I was just wondering since that was on the homework, it was 7.
But I didn't have an x up here, did I? What did I have?
Yeah, log 7x.
Oh, 7x like that? Okay, then yeah, the answer here would be x.
Oh.
Because see, they're the same. Same base, same base.
So why is it different?
Okay, those are the first 3 properties. We good? All right, the next 3 properties are going to look way different than these 3. All right? And these properties are properties that it's not going to be as easy to explain. You're just going to have to almost take these on faith. The first one says this: log base a of x times y equals log base a of x plus log base a of y. Now, I realize that looks ugly. And we're really not going to use this property, all right? But to be somewhat thorough, to get to the property we need today, I'm going to list the 2 before it that we usually use. So what this log says is the following. If you ever have a log, it doesn't matter what the base is. If you have 2 things being multiplied inside of this log, that you're allowed to split this log into 2 logs. See, 2 different logs, and create addition between them. And just put the first factor, which is the x, into this log, and then put the second factor y into this log. Okay, this is an important property if you were actually going to go do like more math. This property of log allows you to split logs up. The next property, let's see if you can reason through this one. What if you have, instead of multiplication inside, division inside? What do you think happens? It's subtraction instead of addition. It still becomes 2 logs, just like this one. See, 2 logs, but subtraction instead of addition. That's the big difference. You see it? Addition here, subtraction here. It's the only difference between those 2 formulas. All right, and now the big formula that we need. This is the one we need. That's 6. Log base a of x raised to the n power. Okay, so this is kind of like what you just asked about. Okay, this is kind of like what you just asked about. This becomes n log base a of x, and that's multiplication right there. So if you want to see what this property is saying, I know it looks strange, but notice these bases, this base and this base are not the same, right? Like if this was A and this was A, then the answer would just be N. But because these are different, what this property says is that you see this power up here? You can just pop this power out in front as a number and then multiply. Now again, these three properties I'm asking you to take on faith more than me showing them to you, like where they come from. All right, so let's do something for this property. I'd like to do the same thing I did a second ago. I'd like to do our special logs with this property. So if I had just log, right, without the base, that would mean log base 10. If I had here something like x to the n, according to this property, I can do what with the n? Move it to the front. It's n times log x. Understand? Powers drop out in front of logs. And then if I had the other special log, which would be the natural log of x to the n, again, the n would drop out, natural log x. And this is the one we need, all right? That's the one we need. I mean, I could have just told you this, or I could have just said, hey, everyone, this is true. But I wanted to give you some of the other properties. I know some of you are going to do some math later on, so at least you have the other properties up there. All right. Let's see how we're going to use this. Y'all ready? That property is all I'm going to focus on right now. I want us to take a look at the following equation. I'm going to ask you to solve an equation. I would like for you to solve the following. 2 to the x equals 8. I want you to first do it mentally. Just think of what the answer is. Yeah? What is it? What is x? X is 3, right? Because isn't 2 cubed 8? 2 times 2 times 2? So we all know the answer is 3, right? But there has to be some more like systematic way of doing this. Because what if this was 2 to the x equals 5? I'll put that one over here. We'll just compare these two. This one you're not going to be able to just think and tell me the answer, right? So maybe there's a more systematic approach, right? So what I'm going to do is I'm going to look at this and I'm going to say, all right, well, the x I'm trying to solve for is up in the exponent, right? And that's a problem. We've never had that before. That's what I was referring to earlier on that word problem. That r was up on the top. How do we solve for it if it's trapped on top? Well, this property right here, the big idea behind this property is that if I have a log in front of something and there's a power, this allows me to pop the power out to the front, doesn't it? That's what this property is saying. I mean, forget the letters x and n. Just the idea is that if you have natural log of something, who cares what it is, and it's raised to something, that I'm allowed to pop this out. That's the property that we need. So when I look at this, wouldn't it be really nice if I had a natural log in front of this? Because then I could pop the x out, right? But I can't just like introduce a natural log out of nowhere. Since it's an equation though, we can do what we've always done, right? The same thing to both sides. So at this point, I'm going to rewrite this equation and I'm going to introduce the natural log function on both sides of the equation. So I'm going to take the natural log of 2 to the x here, and then on this side, I'm going to do the same thing, the natural log of 8. Does everyone see all I've done is introduce the natural log function to both sides? And just like we did before in other equations, you know, as long as you do the same thing to both sides, we're good? Okay. Now, according to this property, and I think you might get confused with the x's, so think of this one instead. If you have natural log of something to a power, I can now drop the power out, can't I? So I'm allowed now at this point to take this x and drop it out in front. And that's what my next line is going to be. So I'm going to put x times natural log 2 equals natural log 8. Do y'all follow that? Yeah? Now, I want you to actually think about these two pieces right here. Natural log of 8 is really asking you what? This is why I hate this notation. E to what power is 8? And this is actually asking you e to what power is 2. So this really is a number, isn't it? This is just a number. And this right here is just a number. And then I have x. So if I want to know what x is, can't I just divide by natural log 2 here and divide natural log 2 here? Since that's really just a number? Let's do that. So my next line looks like this. X times natural log 2 over natural log 2 equals natural log 8 over natural log 2. These cancel. I get x equals, and then I'm just going to need my calculator. I need to be able to do natural log of 8 over natural log of 2. Well, I need to. You need to be able to do that. I'd like to know what your calculator gives you when you do natural log 8 over natural log 2. Does anybody get like 2.99999, or are you getting 3? You're getting 3? Some calculators will round too much, and you'll get like 2.99999 something. That's okay. I wouldn't take off on the test, okay? Because there are limitations to what a calculator can do. But most of you are getting 3? Yep. And isn't that what we said the answer was? Yes? We said the answer was 3. Now I realize that's the long, hard way to do it, but that's because we knew what the answer was to start with. Let's try a problem that we don't know the answer to, like the one we just did, the one that I put up next to it, which was what? 2 to the x is 5? So if I want to do 2 to the x is 5, and I ask you to solve for x, then when you look at this, the first thing you realize is that the x you're trying to solve for is up in the exponent. You say, the only way I can get that x out of there is to come in with natural log on both sides. So I bring in the natural log on both sides of the equation. Don't forget, both sides. You can't just do it to one side. That allows me to drop the x out. And then after this step, I would divide by natural log 2, right? And you get something approximately, it's going to be a decimal. 2 point what? 2.32 approximately. Everybody able to get that has their calculator? Now let's just think about the answer. Does this answer actually make sense? We're saying that 2 raised to the 2.32 should be 5. Okay, well, what would 2 to the 2 be? 4. And what would 2 to the 3 be? 8? Right, see, this is between 2 and 3, isn't it? And if we plug in 2, we get 4. If we plug in 3, we get 8. So 5 is in between those, and so it makes sense that this would be a reasonable answer, right? Like if you got this answer and it was like 20, 25, you know, something's wrong. Something is wrong, right? All right, let's crank it up a little bit. Let's try something a little harder. Let's solve four to the x plus 3 equals 7. I want you to solve this for x. So you look at it, you say, x is up in the exponent, right? The only way I can get x out of an exponent is if I introduce a logarithm, right? So you're just going to take log on both sides of this equation right now. Let's put a natural log in front of this. And then put a natural log in front of this. Y'all good with that? All right. Now this problem is different than the last one. What is going to drop out in front?
X plus 3.
The whole thing, x plus 3. And if you're going to drop the whole thing in front, You better wrap it with parentheses because it's two terms, isn't it? So my next line is going to look like this. X plus 3 came in front. I have natural log 4 equals natural log 7. Now what? Divide both sides by natural log 4. Okay? So if I divide out the natural log 4 on this side, I divide out natural log 4 on this side, what will still be on my left side? X plus 3. And on the right side, you're going to get a decimal. So what's the decimal you get? 0.3? Something like, okay, so I'm not going to be real critical on how far you round this, all right? That okay? Now, I want to know what x is. Right now you're telling me x plus 3 is this. I don't want x plus 3, I want x. So now you're back to a linear equation. Subtract 3 on both sides. And you get x is approximately negative 1.6 approximately. You're taking 1.403 and subtracting 3. Now let's just see if this makes any sense at all. If I take this answer, negative 1.6, and put it right here, negative 1.6 plus 3 is going to be about, I don't know, what is that about? 1.4-ish or so. If I raise 4 to the 1.4, I should get 7. Does that make sense to you that that would be right? What's 4 raised to the 1? 4. What's 4 squared? 16. So it should be in between those two somewhere. So the answer makes sense. All right, let's try a different one. How about this one's going to be interesting. E to the 4x minus 3 equals 5. See, there's nobody in here that can look at that problem and tell me what that answer is. I can't even look at that problem, you know? I mean, that's just impossible to just look at and know the solution. So it's not like this one, 2 to the x equals 8. It's not like that. We can't just look, oh yeah, 3. This, not happening. All right, now I want to see what you do on this, because this is going to be really interesting how y'all handle this. What are you going to do on both sides? Natural log, right? Same thing. The x you want is up here. So you take natural log of e to the 4x minus 3 equals natural log 5. Do y'all agree with that?
Yep.
Okay, drum roll, please. Thank you. I wasn't actually expecting a drum roll. That's very good. Who's going to tell me what the left side is? 4x minus 3. How is that? Wasn't that one of the properties of logs? I mean, you can look at this several ways. You could drop the 4x minus 3 out front, right? If you did that, if that's what you did, 4x minus 3, if you drop it, what would be left out here? ln e, right, would be what's left. And then equals ln 5. And what is ln of e? 1. So it's really not even there, is it? That's one way you could look at it. Another way you could look at it is this property. What's natural log of e to the x? X, right? So if you look at it this way, what's natural log of e to the x? That's the whole x, right? Natural log of e to the stuff is going to be equal to the stuff, right? So you could just say, you could go directly from this line right to 4x minus 3 equals natural log 5. Either way, right? You go this way, that's going to turn into 1, and that's going to take you right to this, or you just go straight from here to here. Y'all okay with that? All right, how do you solve this? Yeah, there's several things you could do here. Why don't we figure out what natural log of 5 is on the calculator? What's natural log 5? 1.6? about 1.6. And from here on out, we're approximating, right? Because we're rounding it. And now this is a linear equation. Solve it for x. Add 3, divide by 4. So I'd add 3 on the next line. When I add 3 to that, don't I get 4.6? And then I divide by 4. And that's going to go in there, what, 1.15? Good enough? 1.15-ish. Any questions? Now's the time. No? You're good? Okay. All right, I'm going to give you one more just to see how you handle this. I think we'll be ready to answer that question after this. All right, how about this? How about 4e to the 6t plus 7 equals 20. And I want you to solve for t. I'm using t instead of x, all right? So you look at this and you realize, wait a minute, the variable I'm solving for is up in an exponent. I'm going to need a natural log. The question becomes, when do you apply the natural log? And if you apply it right now, you're going to be in big trouble. It's not going to work. You have to isolate, okay, this is very important. You have to isolate the factor that has the base and then the variable in it. You need to isolate that factor before you come in with the log. So naturally, to get it by itself, all right, so I'm trying to get this thing right here. Not even the 4 in front, okay? Just the e to the 6t, I want to isolate it. So subtract 7 on both sides first. So if you subtract 7 here, it goes away. Subtract 7 here, you get 13. So I have 4e to the 6t equals 13. Are you all right with that? Almost isolated. I still have this 4 in front, don't I? How can I get rid of that 4? Divide by 4, right? Because it's being multiplied. So divide both sides by 4, and you're going to need your calculator at this point. Let's get decimals here. E to the 6t equals 13 divided by 4 is 3.25. Oh, my phone's not turned off. I confiscated it. Okay, you ready? Keep going. Now you're at the stage where you can do what we did in the last problem. You can do the natural log on both sides. And right away, immediately on the left side, something really good is going to happen, right? As soon as we see natural log of e, we just get happy inside. Because really, everything's going to go away, and that's just going to drop out by itself, isn't it? The 6t is just going to wind up being alone. So 6t here. And then I get on my calculator and I do natural log of 3.25. And I get, you get, what is it? 1.17. Okay, so we're going to do approximately 1.17 or 1.18. Either way, good enough. And finally, divide by 6, both sides. So t is approximately, what is it? 196. There you go. All right. This all makes sense? Now, just so you know, the way I showed you to do this is by doing the natural log on both sides of the equation. It actually turns out that you could do log base 10 on both sides. You could do any log on both sides because this property is still the same, that it's going to drop out. The reason we use natural log is because, number one, you have that key on your calculator. And number two is that if we ever get faced with E, it's going to be a pretty nice result. And will we ever be faced with E? Well, yes, because in financial models, we use E all the time. In physics, E all the time. So it's just, It's just best to come in with natural log on both sides. All right, let's go back now. Let's revisit that problem where you put that money in the bank. You wanted to double your money in 5 years. So you're going to go see if you can find the interest rate, right? So we were at this point. We had 16,000 equals 8,000 e to the 5t. Wasn't that where we were? 5 what? 5r. You're right. Thank you. 5r. T was 5. Okay, I'm going to give you a minute to see if you can come up with r. Do the same thing that we just did. My hint is to isolate that. You got to isolate that piece first. You got it? Let me see. Let me come over there. I'm going to see what kind of interest rate you need. Is it doable?
Really low. When I divided that, I got 2.
Mm-hmm.
Canceled out. The L in 2 is 0.69.
You divided by 5.
I divided by 5.
Okay. We'll see what other people get. You might be rounding a little bit too much. Maybe go out in 2 or 3 decimal places. I'd say 3 for this one. Do you get something yet? Okay. When you get an answer, let me know. I'll come by and see if I agree. That's what other people are getting. Yeah. What do you get? Yep. Okay. Yep. That's what I'm seeing. Yep. You getting anywhere? Getting anywhere? Try and get that E thing by itself. Divide by 8,000 first. Naturally. Yep. Okay. You're on the right track there. How are you doing here? You're trying to get this by itself, right? Trying to get that by itself. You don't want this here. So how can you get rid of this on this side? Divide, right? So divide 8,000 here, divide 8,000 here. Yes, yeah, sorry, I saw it, it looked good. Right? We at the same place? 2 equals e to the 5r, right? And now, natural log on both sides. Natural log 2 here. Natural log e to the 5r. And what happens to the right side? Right? What happens here? What do you get? You don't know. When you see natural log and e together, they go away basically, and this just falls out. So you're just going to get 5r on this side. Okay? That's the property you have to be aware of, 5r here. This is natural log 2. So can you get natural log 2 on your calculator? What did y'all get for r? Approximately 0.139, right? Something like that? Once you do natural log 2, divide by 5 on both sides. So what does this mean? We're going to go to a bank. We're going to look for an interest rate of 0.139%. Oh, wait, no, we have to convert this to a percentage. This is the decimal. We have to convert that to a percentage. So the interest rate we're looking for is approximately 13.9%. Not happening, right? But that gives you some idea. Now, I haven't done any research lately, but I heard that the stock market is usually long-term is somewhere between 8 and 12% return. Well, it all depends on how you invest, but over long term, and 8 to 12 is reasonable. So the stock market is somewhere where you could double your money in 5 years, but you could also lose all your money. So it depends. High risk, high reward. Does that make sense? how we did that? So here's another question for you. Let's kind of switch it up a little bit. Let's, instead of looking for an interest rate, let's talk about time. Okay, you invest, let's say you put $2,000 into a CD at an interest rate of 1.35%. Okay? A CD at 1.35%. Interest is compounded continuously. And when you see that word, you should be happy, because that means E is going to be there, and you're going to be using natural log, and so you know good things are going to happen, right? How long, bless you, how long will it take to double your money? So you basically want to know, at that interest rate, if you just go put $2,000 in, how long is it going to take for you to have $4,000, right? That's what that means?
10 years.
So let's see. What is the formula I'm going to use? PERT, right? That's my formula. Which of these pieces do I know? A is what? 4,000, because I'm trying to double my money. Everyone aware of that? So this is going to be 4,000. How much is P? 2,000. E is always E. Do we know the rate? 1.35. But we have to convert it to a decimal. Don't forget that part. So it's actually 0.0135, isn't it? That's what R is. And what else? T, do I know T? I don't know T, but isn't that what I want? See, because it says what here? How long, right? Time-wise. How long is it going to take? How much time is going to go by? See if you can solve that one. And when you get an answer, let me know. You got something? I don't know. I haven't done it. I'm going to see what everyone gets. Did you get 55 years? No? What did you get? 5,000 years? I'm not saying that's wrong. What did you get? 55?
51.
51 years?
51.
Take your time on it. Take your time. 51 years? Look, it's looking like 51.3-ish. Yeah? 51.3? Yeah? You got 59? Oh, 51. Okay. I'm going to work it out up here. If anyone's stuck, I'm just going to work it out real quick. I'm trying to isolate this piece right here. So I divide both sides by 2,000, and I get 2. I take natural log on both sides. And then from there, the left side's natural log 2, and the right side is automatically this. And so I'm now going to take natural log 2 on my calculator. 0.69? 0.69 equals 0.0135t, and I divide both sides by 0.0135, and I get about 51.11, but look, it's approximately because we've rounded quite a bit. And so the moral of the story is, don't do that, right? You've locked your money up for 50 years, and when you get it back, you're going to have twice as much as you had. But 50 years from now, how much is $1,000 going to be worth? You know what I'm saying? Like what you can buy now for $1,000 versus what you can buy in 50 years for $1,000. You probably lost money, didn't you? You probably lost money. If we're even around in 50 years. Okay. What do y'all think of this? Pretty straightforward, or you don't like it? Hey, I'm curious. Would anything in the problem have changed? Y'all pay attention to this, okay? This is actually, I want to get to something here. Would anything in the problem have changed had I changed this 2,000, let's say, to 20 million? What do you think? You think it's going to take longer to double our money? Less time? How many years do you think it'll take to turn 20 million into 40 million at the same interest rate? Or the same amount of time? Do you think it's the same amount of time? Take a look at this. What would happen? What would change in the problem? This would become, I added 1, 2, 3, 4 zeros here, 1, 2, 3, 4 zeros here. But when I do my first step and divide on both sides, this is still going to be 2, right? That's still going to be 2. So everything else is exactly the same. You get the same answer. So it does not matter actually how much money you put in. It's going to take the same amount of time to double your money at that rate. What we were talking about the other day about winning the lottery was that if you have enough money, even if the interest rate's low, what they're going to pay you for that money is still a lot of money. You know, so you're going to be paid a lot of money for the $20 million, but it's still going to take you 50 years to get to 40 million. All right. This formula, this PERT formula that we've been using, is a financial model. That's what we use in finance. The amount of money we have at the end is equal to the amount of money we put in times E raised to the R times T. T is time and R is the interest rate, right? But there is a similar formula that we can use. I'm going to put it right here. And it's almost exactly the same. I just changed some letters. Instead of using instead of using P, I put A with this subscript 0. I'll explain what this means in a second. And instead of using R, I put K. And this right here is what we use for, bless you, this is like a more general formula than this one is, because this is not tied to finance. If you want to make it a finance problem, you replace that with P and you replace that with R. But in a more general term, these two things take on a different meaning if you take the money out of the situation. All right? This A naught, sorry, that's how you say that, A naught. Not meaning 0, I think is German. Is it German? Not? 9 is German. Yeah, okay, so anyways, this right here is your starting amount. And this right here is your ending amount. It's just like the money, right? And this right here